Okay, so I think it's probably about time to get started. Otherwise, I'm going to wind up over time. So, my name is Heather Miller. I'm a PhD student at EPFL. I'm in the Scala group with Martin Odersky as my advisor. What I'm going to talk about today, so this is the advanced session. This isn't extremely advanced or anything. This is a research project, but that doesn't mean it's scary. It's kind of, today what I'm going to talk about is more of an idea of a model. Something that, in this talk, I hope just to give you some intuition. So there's not going to be anything super intense or researchy or scary in here. It's more like, hey, there's this new programming model that we thought of. Here's the intuition behind how it works, and I have lots of little animations and things so you can kind of see how things happen. So it should be actually quite easy to digest. So function passing. It's actually, I think we should call this function passing instead of function passing style. It's a way to do distributed programming in, I think, a more typeful way than tends to happen most often. And it sort of is based on two projects that I've worked on throughout my PhD. So the first one, some people might have heard of it, it's a serialization framework, we call it pickling. The idea behind this framework is that we use the types of the things that you're trying to serialize at compile time. We try to generate performant picklers, and you can swap in and out formats and things like this. So you can even change the representation of things, and because in the best case, when we can generate a serializer for your type that you're trying to serialize, of course we're inlining it and things, so things get really performant. And like I said, we can swap in and out different formats, so it's actually also kind of flexible. Another project that I've been working on, which is sort of, in the same ballpark, is this thing called Spores. It's got a kind of a scary, weird name, but the idea behind it is just that we want to make it possible to reliably serialize closures. And actually, the ugliness in this whole world is dealing with the environment and what your closure is reaching into and crazy object graphs that can happen. So this project, it tries to control that in a way that's sort of intuitive and straightforward. And at the same time, we want to, well, a very researchy side of it was to add like a little type system onto it to be able to control the sorts of types that closures can capture. And this is actually interesting if you're a framework developer like Akka or Spark or something like this, and you want to prevent somebody from capturing the Spark context in a function accidentally, or capturing an actor or something like this. So you can actually put this in the type signature of something and actually forbid client code from developing functions that capture these things. So these are these two projects, and what I'm talking about today, it brings these two things together into a programming model. So it builds on this basis of serializable functions, and the whole goal of what I'm doing is to provide a more typed sort of immutable substrate for people who want to build distributed systems where you want to keep your data as much as possible in one place. And the result, it sort of simplifies the design of a couple of important things that you care about usually when you're building some kind of system. And to me, the most important things are sort of the ability to recover from failures and to be able to debug things that are being sent over the network and all over the place. And what's nice about this model is that it removes as much state as possible. That doesn't mean that all distributed systems should be, realized in this model, because many distributed systems need state. So in ones where you can sort of remove as much state as possible, I think this is a nice model. So this is also a research project, which means this is like pie in the sky kind of, hey, let's just, talk about it and think about it and see where it goes. We've built it, we've changed the design many times. We're iterating on it, and it's all under development, and we've written a paper about it all. At the end of the talk, there's a slide with the URL if you're interested in reading it. And I also have to thank Databricks because they allowed me to do this under their wing for a few months. So something like 30% of my time I was working on this kind of stuff, and it's just research. It has nothing to do with anything that they're doing. So it's nice of them to let me do it. So the fundamental idea of this model is to invert the actor model. So it's kind of like a dual to actors in some very loose way, if you want to think about it that way, if you want to walk away with anything. And, okay, so how? If you think about actors, they encapsulate state and behavior. They're usually operating on some kind of mutable state somewhere. Well, they don't have to, they can. And they have a message handler, they stay in one place, typically. And basically what you're doing is you're exchanging data and commands back and forth over the network, right? So you keep your you keep your functionality typically in one place and you're sending your data around. And the function passing model is exactly the opposite. So there is no state that an actor is managing. Instead, you can think of this as like a distributed sort of persistent data structure, but something very simple, something small, not the size of something like Spark, but like a kind of like the size of like a middleware or something like this. And the idea is that your data stays in one place, you don't move it around, typically. You can if you really have to. And instead, you pass functions around, so you can give your users the ability to define functions to operate on your data all over the place. And this is also, just to keep things clear, this is not a new concurrency model or a new model of concurrent processes. Instead, we're just proposing a new way of working with distributed data in a way that's a little bit more functional. And I have to bring this up because, this is an old paper. I don't know, has anybody seen this before? I'm sure people have heard of this. Anybody here? Oh, not so many people. Okay, cool. So this is a note from the 90s. It's more of like an essay about a number of things that happened whenever trying to build typically distributed systems. I'm just going to bring up two quotes here because they bring up sort of important things that we haven't necessarily learned yet, I think. This paper is mostly commenting on the idea that you can hide distribution by operating on what looks like a local object but doing sort of remote computation, things like this, right? And so they say there are four things that are important: latency, memory access, partial failure, and concurrency, that make merging of these models of local and distributed computing not a good idea, basically. Whoops. Oh no. How did that happen? All right. And instead, what they suggest is a better idea is to accept that there are differences between these two things, latency, memory access, and all of these things. These are big differences, and that all stages of development, the end user should be aware that there's a network in between what you're doing, and that things can fail. You shouldn't hide this, right? And so rather than trying to merge local and remote objects, engineers should be constantly reminded of the differences and know when it is appropriate to use each kind of object. So make that a part of the programming model. And so sort of this basic idea is kind of what we're also trying to present in our model. We keep these things in mind when we design this. So rather than get into a bunch of philosophical detail from notes from the 90s that we haven't really learned from, instead I'm just going to give you a little illustration of what this thing looks like. So there are two concepts. Like I said, this data that sticks around in one place, it's immutable always, and these functions that you can move to the data. So I have no better name for this right now, but throughout the presentation I'm going to be calling this immutable data silos, and the functions that you can move around, as I mentioned, these things are called spores. So that's what they're called. So I'm just going to start by describing what this silo concept is in case, okay, so here's a picture. This thing on the left is a silo, and the thing on the right is a silo ref. You can think of these as kind of like actor refs, but to a piece of data instead of an actor. You don't actually, see I have master and worker here. That actually doesn't matter. These things don't have to be master worker. They can be peer-to-peer. You can have on this worker machine here, you can have a silo ref pointing to what's called the master machine. You can spread these out in any way that you'd like. And the idea is that you do computation on this silo ref thing, and depending on what you do to it, it's like I said, it's built into the programming model whether or not network communication happens. But whoops, there's an illustration. Oh, here we are. You use this silo ref thing and you apply functions and things to it, and stuff gets sent over the wire, and over time you have an actual sort of big chunk of data being materialized in sort of a tree form right on the other side of the wire. And like I said, the silos don't have to live on the same node. So that's just a quick picture. There are three important operations on these things. We're also renaming these things all the time, but the point is just to kind of get an idea of what these three things are. So first one, first of all, we know that there's this silo ref thing, and these methods are only available on the silo ref thing. You don't actually have any way to touch a silo in any other way. You just always touch the silo ref thing. And there's a method called apply. This is actually also, we have a variant of this that's a little bit simpler, but I'm going with this thing that takes 2 spores right now. It can take just 1, and that's actually in the final design, but this right now is just for the sake of illustrations, so that later you'll see an example what we're doing here. But imagine it takes 2 spores, or 1, and it returns a siloref. So this is like you can think of this as a lazy combinator. The idea is that maybe you want to apply some functionality to some remote data, and you get back a siloref. So that whatever you're applying to some data could be long running, you don't know. But you want to basically keep the data on the other side of on another machine, right? And so you can implement things like if you think of like a distributed collections abstraction, you can implement like Spark's map, for example, with something like this. And what it takes is so these 2 spores. In this example, like I said, just imagine it this way, where one is like framework logic and another, so one is like the actual map logic, and the other is sort of the function that you would pass to a map. And the idea is that, like I said, it defers the application of that function to until you actually eagerly send it over the wire. And this silo thing, like I said I showed in this earlier illustration, it eventually gets materialized. Send. If you are familiar with, actually this is really nice to use Spark as an example. This is like an action. So this forces things to be sent over the wire. So if I've queued up a bunch of these, a bunch of functions via the supply method, send is what actually forces it to go over the wire. And basically, it waits, well, it doesn't wait, it's asynchronously completes a future, basically, with the result of whatever computation has been queued up. And actually this one is quite important, and maybe it's a little bit counterintuitive. Right now we're calling it a flat map because it basically is a flat map. Instead, so it takes a spore and a spore from some type to a siloref of some other type. Typically these things are collections, they don't have to be. But the idea is that you send a spore to a silo of the receiver, siloref, whichever one that you've called it on. And the result of applying that spore is a siloref whose contents should be made available in a new silo on the same node as this, and it returns a new siloref. So this is basically, and also this doesn't have to, so this is important, it doesn't actually have to be the siloref that it's related to doesn't have to be on the same node. So this is actually useful in the case that you need to do some sort of shuffling-like operation, in case you actually have to move data around from one machine to another. Think of, there's a number of operations where you need to sort of group pieces of data onto one machine. And this is the sort of operation that you might want to use to do that. So I gave you these functions, I gave you this very vague picture earlier. Let's make things a little bit more concrete. So let's say you have a siloref of some type T, which points to an existing silo of T. So the way that you read data into these silo things, you read them in via these silorefs, but they would typically be filled with some sort of data from some sort of persistent storage or something like this. So what happens, let's just say you have some function that you want to apply to this silo of T. You send your function over the wire. It goes from T to S. If I didn't show you that. Hold on. So yeah, this function goes from T to S. Let's say. What you get back on the machine that you're operating on is a siloref of S. Actually, it doesn't have to, so this actually wouldn't be just an apply. This is like an apply and a send. So maybe I didn't call send. This function would be queued up, basically. It wouldn't be sent if I didn't call send. And instead I would end up with still this siloref and not maybe necessarily anything being materialized on the other side of the wire. Eventually, though, whenever this function is sent over the wire, like it was in the illustration, over time you eventually get a new silo of type S, which is materialized on the other side. And eventually, this reference here will point to this thing here. You can actually, if this thing is ready before this thing is, you can queue up operations on your siloref, and the runtime takes care of eventually sending them over the wire when this guy eventually is materialized and it can receive and be operated upon. So these things can exist in all kinds of configurations on many machines, and like I said, they can be peer-to-peer. They don't have to be related to the same sort of tree of operations. Yeah, and that's sort of like the high-level intuition of what this data things do. So there are these other things called spores. I told you that they're functions that can be serialized and sent over the wire. I'm going to go into a little bit of detail about what they are. I'm not going to delve too deep. But what do I mean exactly? So a spore is this is what they look like. This is the ugly sort of longhand definition. There are implicit conversions to shorten things up a little bit, but this is what they look like in general. So you have this spore keyword thing here, or not a keyword, but a spore like identifier thing. And you have an environment, a spore header, this H, represents this first part, which is the spore header, and you have the actual closure itself. The rule is that the closure can't capture anything except for what that environment that you explicitly declare. So in this case, it captures this helper thing, right? It fails to compile if you capture anything outside of this spore block, basically, and that's the basic rule. So what this does is it requires you to explicitly declare your environment, so you always know what your closure is closing over, and you are never surprised by some crazy object graph that ends up happening. So this forces a sort of syntax that keeps object graphs a little bit clean. There's a little bit more to it. Another thing that this provides, so all captured variables that are declared in this spore header, or there's another thing called capture, which I'm not going to get into today. Anything that's captured in this environment explicitly, the initializers of those things are called and executed once upon creation of this spore. So you don't have the situation where your environment is over time initialized and changes, basically, which is kind of important. It gets difficult to reason about when you have something, an environment changing over time, especially when you want to send it over the wire. And as I said, references to captured variables do not change, right? So another important note about this, so we're not doing any sort of magical transformations here. If you remove the spore marker on this block thing here, so if this is just the same code but without the spore here, the evaluation is exactly the same. We don't do any magical transformation. And like I said, spores and closures are related. You can write a full function literal and have it like implicitly converted to something that would expect a spore. So if you had a method that takes, so let's just say you have some sort of distributed collections abstraction and you want it to take a spore because you don't want your users accidentally passing bad things into it, because in your type signature you say spore, somebody can still pass a function literal and you can this thing would be implicitly converted basically to a spore, and the checking would kick in. So it doesn't get actually very verbose either. And the benefits of doing this is that, like I said, this environment or these captured variables that you've explicitly declared are fixed at the time that the spore is created, and you can statically ensure that everything that you capture is serializable via this serialization framework. I mean, this is not an explicit requirement. You can still use this with Java, but that's sort of a nice benefit if you use it with the serialization framework. And there's a lot more to read about this. There's some details. I mean, so like you might have some questions like, well, what happens if I capture a lazy var or something like this? Well, you can't. There are some rules, and there's more details in the paper if you really want to see. There's also a SIP. If you go to the doc site, there exists this specification that's a little bit easier to read if you want to know more. So I gave you these two things. Maybe I can give you an example that makes things slightly more concrete than before. You have to think about this example in a kind of a weird way. So let's just say, I'm just trying to show you a picture of kind of inside what would be happening. So let's assume that you want to do like a distributed list kind of thing. So imagine like a list or an array or something like this distributed onto different nodes, and you want to do a map and a reduce on your distributed list. Let's just say that you already know how to do a map on your distributed pieces, and you already know how to do a reduce, and you've implemented this logic. Using these, you have these pieces of data that you can access, and you implement the logic to do the reduce, for example. These things have to be spores, as I mentioned. You saw the type signatures earlier on in the presentation. And let's just assume for now we have these things, okay? So I'm just going to show you what it looks like evolving in space if you wanted to do, for example, a map and a reduce on like these little. This would be like one. This example here would be like one shard of it, right? The idea is that so again, you have this apply function, which for the sake of illustration, it has this logic for doing the distributed map, like the logic for doing the map function on your distributed data. And it takes also another function, or another spore, which is of type f. And this is the user-provided function to your higher-order function map, right? And again, there's a version of this where you don't need 2 spores, but like I said, for illustration, just imagine they're necessary. And what happens, you kind of create this persistent data structure where you have this let's just say that you have a silo ref of type list of int, and you know how to read in this list of int, and this is the sort of the root node of your kind of persistent data structure. When you call apply, basically what happens is you create a new node, and you have these 2 functions, or these 2 spores rather, that are contained inside of this node in the graph, right? And you can keep doing this, where you keep on applying things, and like I said, when you use the apply function, it's lazy, it just kind of queues it up. You're kind of staging your computation in some sense. But let's just say you need to do a reduce now. This is when you would do the send operation, right? Because it's an operation where you need something back that's not a sort of piecewise transformation on your data. You're reducing, you're aggregating something, and you need something back. So here in this case, let's just say you use your send operation, right? Which is what you want. Same thing. You have this reduce function, basically, that you would pass this with the user-defined function or I'm sorry, actually no, this is from this apply. It comes from the previous apply. Oops. So what happens is the send is called. Your function is sent over the wire. The runtime that manages this machine receives it. It's actually just a very simple thing that receives messages and figures out where to apply them to. Whoops. And then your whole sort of chain of other actual silos gets materialized when you kick off this computation. And when it's done, it sends back the result. When in this case, so we were doing like a kind of like a map on lists of int, and then you would do a reduce and get an int back. And in this case, you're completing, so that the type here, the return type after you would call this send thing would be a future of type int as a result. And so this is kind of obvious, I think, how fault tolerance sort of is simplified here. What you end up doing is you end up building, so we're not actually doing any sort of complex distributed computation. We're basically providing you a nice structure, which is itself a persistent data structure that represents the transformations that you do on your distributed data. So the idea is that you have like a graph of transformations, and if you know how to populate the root node of your graph, you can always just replay these things. And what's nice about it is that actually I should. So the silo and the silo refs are, like I said, a persistent data structure, and that so you can derive the data from this root node, and traversing the whole thing. It's basically just exactly the same as this notion of a lineage from databases, or that Spark uses. So this is a really old concept in the world of databases. And since the lineage is composed of spores, so even the framework logic is implemented in terms of these kind of functions, it means that you can actually persist this very easily. It's guaranteed to be serializable, and you can either save it on the same machine, and we have actually, there's a whole sort of semantics for fault handling, which we've put together in great detail, and I'll show you if you want to see more, where to read more about it. But basically, you can either send, for example, such a chain of transformations to another machine, or you can persist it and keep it on the machine that you're on. And this is kind of nice, because what you get from this is you get sort of the same. You have this model that. It can be peer-to-peer. It can be sort of master worker, and you can sort of decide, for different shards or different sort of trees, or other trees, different sort of chunks of this model that are distributed onto different machines. You can decide upon the fault handling strategy per chunk. And we've actually built some rather powerful things on top of this. most notably, we built a small version of Spark on top of it, which basically has types pushed all the way through. All communication and things are typed. So the high-level picture here is that these data silo things, you can think of them as, so I gave you just two machines, and in this case, you know, your tree of data structure, or sorry, your tree or your data structure representing all of these transformations does not have to span just two machines. It can span as many as you want. It doesn't have to be like a distributed collections abstraction. You could be wrapping some way of accessing some sort of data store somewhere and be coordinating between data stores with this thing. It's not necessary. I keep on using this example of a distributed collection because it's very straightforward and everybody understands it, but it's not limited to that. It can be, like I said, used to do these sort of coordination between different sorts of data stores. And the cool thing about this is that since everything is sort of this persistent, like, you know, immutable sort of data structure, that where sort of the transformations that are done upon it on your pieces of data are represented as these functions, you can sort of easily serialize things, and actually there are policies or ways to implement policies for recovering from failures, and everything is serializable, so you can decide, you know, if you want, you know, you can decide to send it to a neighboring machine, or you can you know, save it to disk and restart, or sorry, save it to persistent storage and restart from persistent storage. So yeah, taken together, these things provide a nice way to deal with fault tolerance, and there's a paper that we wrote about it. If you want to see more, it's here. But I think that's it. Usually this talk goes much longer. I don't know why it was so short, but if you guys have any questions, please feel free to ask. Thanks. Yes, actually, I have no idea how to do the questions. I think I should just repeat what somebody asks, so I don't know where to start. You in the front with the green? Oops.
So it's pretty cool. So it seems like the heart of the problem is to figure out how to serialize and deserialize enclosures.
Mm-hmm.
And are you using tasty trees or?
No. I mean, that would be, I mean, that's no, we're just using the serialization framework. Tasty trees are new. That would solve a whole bunch of problems for basically like compatibility and things. It's not, I mean, it's not like we're serializing things into whatever, some kind of tasty tree, and then somehow like you know, like recompiling in another machine, or like swapping in bytecode or anything like this. That's not actually happening. What's happening is that right now this whole thing is basically assuming the same class files on every machine. So we're not actually like swapping trees or bytecode or anything. That's scary. It's hard to make sure that you don't have a bad guy sneaking in some bad tree. Sure.
You mentioned the idea that you use Spores as a point back to say, you can't close the
Yep. Mm-hmm.
How would that work with the scenarios? I saw the idea that you use Spore along each player.
Oh, so this is like, so yeah. So there is a type system and a way to. So these things are actually. I have a presentation about the Spores thing, so I took some slides that are just the high level. I didn't answer these questions that you have, but there is actually the way that we do it is for the type checking we have this type member called excluded, and you can say what you would like it to be. So these things are actually like refinement types, and you would like basically refine the Spore type and then implement the type member excluded with some type that you want to exclude. Exactly, yeah, exactly. There's also one, I mean, in order to do that, you also have to, because one thing that happens is if you want to compose two functions where one excludes something, another one doesn't, and maybe, you know, you might produce something that sort of could then capture like an actor. We have to also keep track of the things that we capture over time. So if you're composing things together, there are two type members. There's one called captured, which has a set of the things that you capture, and then this excluded thing. And every time that you compose things together, you can make sense and reject or not. So yeah, so you don't lose a type constraint over time, basically, which is nice. Francois? Sorry. Wait, so you're talking about the situation where you like destroy memory, right? I'm sorry, I can't really hear you. Map pipeline. So you're making a big chain of map calls, for example, whatever. Yeah, and so you're worried about memory. Oh, the actual closure? Oh, so the thing is this. Because they're spores, you know what you're sending over the wire because you have to explicitly declare it. So the hope is that you can see how big the piece is. So the only thing that oh. Yeah, sure. I guess one could do that. I mean, I don't foresee it being okay. True. Well, yeah. So the class files are shared, but the environment is not. That's the thing. So if the function that you want to send has a humongous environment, let's just say you explicitly capture, I don't know, a megabyte of Wikipedia for some reason, in an application like Spark Streaming, you wouldn't want to just keep on setting the same environment over and over again. I get your point. We haven't thought to do that. I get it. Yeah. I mean, that's a sensible idea. We haven't directly focused on the streaming case, but yeah, that would make sense if you wanted to do something like that. Wait, actually, yeah, you had a question.
It sounds like this would be a good general purpose layer underneath Spark.
I mean, so this is yeah, it would maybe not to do much more than make sure that there are types throughout the stack and that communication between nodes is well typed. This is not something that is heavily, crazily optimized. This is a programming model. It doesn't, I mean, it is very similar to this lineage thing is exactly how, frameworks like Spark would recover from failures, right? But the whole point of this is to be a little bit smaller and more free form. So you don't have to be, so Spark has this master worker model where you have basically, roughly the same size shards of data all over your cluster, and you're doing the same thing to all of them. This doesn't support just that model. You can have just some data that's totally different from this data, and you want to do different things with it, and you maybe want to coordinate between these two machines doing it. I keep using the Spark example because everybody is comfortable with it, and it's very easy to map it to this. But it's not limited to that. You can do other things with it. So I mean, exactly what you might want to do with it, we have just a bunch of toy examples worked out. So like I said, coordinating between two totally different things where you're in the middle, managing them. That's one example, but that's not the only thing that you can do. Yep.
So you've described the coupling between the two machines and two computations. How much can you separate that in time? Can that be something where you have, say, a log, a message log that represents that state that you picked up later? Fault tolerance seems to suggest that.
I'm not completely sure I understand. Could you try to rephrase it? So you have the two machine case of doing different things. Is that what you mean?
And so you're describing the interaction between them in terms of the context of one being essentially assumed by the other in terms of the side.
So you would in this case if one are you asking about dependencies upon each other?
Well, yeah, I guess I'm asking how much that would be made asynchronous.
Oh yeah, I mean I think maybe I wasn't completely clear about one thing earlier in the talk. So this is all asynchronous because you have everything is based on sort of laziness and futures. So you have these two operators that you would use. You would use, where is it?
I guess
Hold on.
How far can you push that though? Can you do that in the absence of one of the machines being live? And
Yeah.
this becomes a set of messages that will be then resolved by the system later.
So okay, I see what you mean. So this depends on the fault handling policy that you create. So there are ways to. So in this case, you want to, in as many places, keep track of these transformations that you. And we have also ways where you monitor for failures. So you can have neighbors monitoring for failures and restarting other neighbors and things like this. So I think to answer your question is you have. In terms of the fault handling, it's totally asynchronous, and you can like like I said, everything, you have these like failure notifications, and you can implement when you create the root node here, you implement sort of the fault handling policy, whether you're going to get it from a neighbor or you're going to get whether you have like a master or something like this, like monitoring you and restarting you. So I mean, these things exist. I didn't cover them because it's actually like a I mean, we actually, I figured this would be kind of hard to visualize already, so I wanted to keep it simple so you could visualize sort of how these things would happen. But yeah, there exists a way to handle these faults in different ways. Yep.
Seems to me a lot like free-one-hand work, where you're defining an abstract rate computation.
Yep. Yep.
So I wanted you to say two questions, thinking about that. The other question is, you have this distributed system that says you can't share something exists on,
Yeah, actually, this is what I wanted to bring up that I realized I didn't make very clear. So there are these three operations, and the two kind of important ones is this like lazy-ish apply thing and this send thing. And you can kind of think of these as views. If you guys know, does any people know what views are, where you sort of queue up computation and then you force it later? It's not distributed, right? So this can kind of be thought of as a more distributed version of such things. So in this case, you're actually using this like lazy thing and this kind of force thing. So apply is lazy and send can be like force. You're actually controlling network communication. You have a handle on it. So it's, I mean, I'm not saying, well, send is pretty explicit, but the point is that this is built into the programming model, so you know when something is being, when latency can be introduced, right? And you can queue things up to save time. You can compose functions together and things like this to prevent, even to get rid of these intermediate data structures. In this example, right? No, it takes a second. There's an example where these things are queued up next to each other. You can use this composing functions together. Oh no, I got to go to the spores. Hold on one sec. In this example here, where these things are all chained together, you can get rid of, you can compose these functions together, and then use sort of this like lazy apply and then force send to eliminate intermediate data structures. It's also one idea.
If you can't show that side, you showed.
Yeah.
The next slide.
Yeah, I know. Oh, there it is.
There it is.
Yep.
In this particular example, are those silos actually created as intermediate silos?
In this case, they are. I'm saying what you can do is you can compose these things together if you want. You have control over that, and you can prevent these things from wasting memory. I mean, you have a handle on it. It's possible. In this example, I mean, just for the sake of showing that these things are materialized when sort of their dependencies are available, it was just to show you that that's what happens. So you can build kind of interesting trees. Oh yeah. Okay. So yep.
Yeah, so right now, just comparing it to the word of SQL, like you said, complex.
Comparing it to what?
The word of SQL.
Oh yeah. Yeah.
Complex code word. That would update the database. Why does it have to be immutable?
Immutable? Well, actually, the only reason why we want the things to be immutable in this case is so that if something fails, it's completely brain dead and simple to restart things. You don't have to do snapshotting. You don't have to keep track of some state. There's no state anymore. You have just some piece of data that exists somewhere, and you just do transformations on that. And actually, all you're saving are the transformations. You're just saving the functions, and you make like a very simple, like the size of a small list data structure that represents everything you want to do to your data. So you actually, pack a lot of work into not very much space, and because your data would be persistent somewhere, you can just replay it if anything happens. Yep. Well.
So I understand that you're using primarily for fault tolerance and not for real-time message passing, but what's the overhead in serializing out to a tasty format and then running them on another thing?
I think that's a horrible idea just because you can't be sure that you're, if you receive some tasty format thing, you can't be sure that they're not stealing your credit card information and buying a stereo system, you know what I mean?
Yeah, I mean,
There's security problems with that. This is, in the 90s, there was this big thing, this big mobile code movement, and it wasn't, I don't know, one of the biggest problems with it were sort of security concerns.
assuming that you are actually using silo refs and you're using relaying as it is intended to be done, what is the one-time overhead of using this versus using just the straight method
Well, so a lot of the time when you're doing so these method calls have a tendency to be synchronous, and this is so far completely asynchronous. So you're just you're queuing up computation, you're sending it over the wire, and the only time that you ever need to communicate back is basically this asynchronous sort of completion of your future, which represents whatever the result of the send is. So it's, I think, a lot more asynchronous than, yep.
I was wondering if there was a sensible way to have a directed graph rather than a tree.
Yeah, so these things,
None of the maps there seem to give you access to two silos at the same time.
well, sorry, continue. So we don't stop you from doing that. You can do that. So so there's this flat map thing where you can access a silo on another node, and this is how you can do things like shuffle. So it's possible. We don't stop you from doing that. There's no restriction. It's possible.
So the idea would be you move the silo locally and then you use different methods to combine the two? Because
I'm not following.
None of the signatures here
Uh-huh.
allow you to take as input stuff from two silos. It doesn't matter.
Well, you can capture a silo and operate on it and things.
Okay, so with the flat.
I'm sorry, a silo ref. I'm sorry. That's very clear. Sorry. Thank you. You can capture a silo ref, not a silo. Silos stay where they are. So you can move silo refs to other machines. It's no problem.
Sure, but how do you, if you have, suppose you have a bunch of, I don't know, suppose you have, a bunch of records for the same customers in two different databases.
Sure. Yep.
Pull out a common set of customers in database 1 and database 2, and then you want to do some kind of, so you've got two separate silos, each with a lot of data. You can co-localize them on the same machine by using flat maps.
Yep.
How would you merge the two?
Oh, okay, yeah, so you can, so silos, the silo that you're so it's not required that the silo that you're operating on be on another machine.
Right. And so when they're local,
Yeah.
how does that help?
Well, in that case, that doesn't win you very much. It's more like you can create a new piece of data on your on the current machine. You have some kind of wrapper if you want to queue up later computation on top of it. I mean, in this case, a silo doesn't do anything for you if you're just stopping there. But
You handle it by hand, pulling data out of two separate silos.
yeah. Yep.
I suppose the collection of the silo refs that
Oops.
silos became no longer required.
I'm sorry. Can you say this one more time?
When you deallocate, when the silo ref gets garbage collected, is there a message sent to?
So right now, we don't do much to help you with garbage collection. The idea would be that, and maybe this is inconvenient and maybe this is not good, but the idea is that you would be able to try to optimize away, like I said, these intermediate data structures, so these things kind of stick around unless, I mean, you can't clear out nodes or anything. We don't allow that because it would make fault tolerance harder. Yep.
How does data move from different machines? For example, if you apply shuffle,
Is it happening in one big block or is it streaming? Yeah. So in the first iteration of this, we had this really weird thing that we called pump2, and it was sort of streaming data, and it required things to be collections and stuff, and it was not exactly the nicest thing. But it's kind of it's a little bit less nice. It's like I said, it's kind of emptying, not emptying, but it's transferring the data iteratively from one silo to another. And like I said, it's based on things being collections. And in the case that you have this scenario, you can iterate through a collection and stream it over the wire. And in the flat map, in the case that it's parameterized on something that's traversable, it would do this streaming, sort of sending it over the wire. Otherwise, it just does it in one big block. So it has these two variants, basically. Yeah. Yep. Oh, good question.
In the scope of the Spore and the fact that
Yeah. Good question. So in the case of, so what seems to happen, or at least one of the, so I had the task at one point of integrating the serialization framework into Spark. And the biggest problem that I had there was whenever anything ever needed to be serialized, which it often is, you keep it serialized in memory, the type information gets lost beyond sort of like the first level. Everything is just a blob of any's and, or things that are totally untyped, and you have this very thick stack of things that you have no idea what it is. So the whole point of the serialization framework was that we tried to generate as much serialization code as possible so that there was fewer runtime introspection sort of tasks happening, fewer transitive closures being calculated, and less time wasted in serialization. So this helps in performance, and it also helped. There was also a number of situations where we would be getting, like, there would be some blob of something that you would be sending somewhere else and you didn't know what it was, and there were like runtime, like class cast exceptions and things like this. So it helps in sort of, you know, 2 dimensions. It helps sort of in performance when it comes to generating serialization code, and it helps also with a little bit of the debugging when you're sending things around.
It doesn't particularly help the program.
It helps the system designer. So this cares more about the system builder. But that's also one type of programmer, and if the system builder designs things in a way where interfaces are very nice, it could help the programmer too, because you keep these types around and you push them all the way through. Yeah. Yep.
So with OOPSLA, with the responsibility, there is a big challenge in trying to problem solve and like work backwards when you when something's not working right or if it's not performant.
Mm-hmm.
Do you feel like this is
So you're like performance debugging, you mean, or?
Performance or something's not behaving correctly or whatnot?
Uh-huh.
Do you feel this is easier to intuit about or you know to problem solve with?
You know, these sort of event-driven frameworks are typically used for kind of different tasks. So I can't really comment because it depends on what you want to do and whether or not, I mean, this could make your task harder or easier if you have something a little bit more reactive, like Akka. You know? So I can't say. Really, it's like really application dependent, I think. Yep. Yeah, just to. So this is all. So in the multi. So what do you mean, like? So this can be, you know, resource management can be as big as a cluster manager. I'm not doing that for you. So in order to start these things up and create them, like to create silos in certain places, you're doing a lot of the work yourself. You know there's a machine that exists somewhere. You have a way to you know get into it. You have like an address and things like this, right? So you create these things that way. And you populate these things that way. So I'm not providing any sort of cluster management framework for you. In terms of scheduling, well, this is, I mean, actually it's quite manual. You're deciding when to send things yourself, and basically, you know, you're like the only scheduling that happens is completing futures here and there, which is, yeah. No, they're much smaller. They're not feature rich in any way. They're just like a container for data that you can sort of like lazily build up and asynchronously complete parts of them. Hmm? Right. Mm-hmm. Well, it depends on what your data set is, right? So if you want to do master worker sort of configuration, you're implementing the logic of you know, you have, you know, this is manual. So the point isn't necessarily, this is not Spark. This is nothing like Spark. The point is to have a collection of, they could be a piece of data that consumes all of the memory on one machine, and you could have partitioned your data by yourself onto 3 machines, but you have references to each of these, and you can queue up, you can build like this little data structure that represents this, you know, these 3 machines. Each of these silo refs point to a different machine, and you operate on them like it's on one machine, right? And it, you know, whenever you feel like it's ready to kick off computation, you sort of send all of the sort of queued up composed functions over the wire and kick off computation. And if you need to get something back, you know, there's this way of you know, sending something back, completing a feature, and returning some kind of result. So it's, if you want to build something like a distributed collections abstraction, it's the world's most manual version. But this is not what it's meant to be. It's meant to just be some way of coordinating between pieces of data. I think we're running out of time, but yeah, we're 5 minutes over. So yeah, thanks.